Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now I'm just going to get started on our set of questions for today's session. Okay, so question number 1 asks, how much does 1 gallon of water weigh? So if we recall the density of water, it's actually pretty easy to remember. It is only 1 gram per milliliter. So if we want to find out how much does 1 gallon of water weigh, we need to know the conversion factor for gallons to milliliters. So let's recall that 1 gallon is equal to 3.785 liters. So to find out how many mils that is, let's also recall that in 1 liter, there is 1,000 milliliters. Okay, so I have everything I need to know to answer this question. So starting off with 1 gallon, I'm going to multiply by the conversion factor to convert to liters. So it's 3.785 liters per 1 gallon. To convert to milliliters, I'm going to put 1,000 mils at the top and then 1 liter at the bottom. And then finally, to convert to grams, I'm going to put my grams on top and then milliliters at the bottom. Okay, so if you'll notice all of the units canceling out, so gallons will cancel out, liters will cancel out, and then milliliters will cancel out. Then if we multiply this through, we end up getting 3,785 grams of water in 1 gallon. Okay, so let's see what the junior tutor said. Weight could mean 2 things. Weight could either mean how it is used in day-to-day conversation, which is the amount of mass in a substance, or how it's used in physics, where weight is the force exerted on a body by gravity. Let's think about the former. This means that to get the weight of water, we need to perform a series of conversions from gallons to the unit of mass, kilograms. First, we need to convert gallons to liters using the conversion factor. 1 gallon is equal to 3.785 liters. Then we convert the amount in liters to meters cubed. Conversion factor is 1,000 liters is equal to 1 meter cubed. Next, we will assume that the water is at normal temperature and pressure. To obtain the mass, we need to convert the unit of volume, meters cubed, to a unit of mass directly using the density of water at NTP. So they have that their density is 998 kilograms per meter cubed. Combining all the steps, they got 3.77743 kilograms. It's pretty much the same. Thus, a gallon of water has a weight of 3.77743 kilograms. That said, we can also consider the second meaning of weight. The unit for this is kilogram meters over second squared, or N. For this, we multiply the mass of water obtained above to the acceleration due to gravity. to get the weight. Okay, so I'm just going to say this answer is correct. I'll also just add that the density of water Okay, I just kind of wrote out what I did. So it depends on what density you find for water. But I'll still say the solution is correct. On to question 2. What is the electron configuration of copper? So copper contains 29 electrons, and its long electron configuration will be 1s2, 2s2, 2p6. Let me just write that. 3s2, 4s2, 3d9. If I were to write the shorthand version of this, I would find the closest noble gas, which is argon. And then I can also write 4s2, 3d9. But we can also write this in a more stable configuration. Since our d orbital, when it is filled, it is more stable than having a partially filled d orbital. So if you take one of the electrons from the s orbital and put it to where the d is, you get 4s1, 3d10. Then I'll just put in brackets that this is more stable. Okay, so let's see what our junior tutor wrote. Copper is the 29th element on the periodic table of elements. There are 29 electrons in the copper atom. Thus, the electron configuration of this atom is 1s2, 2s2, 2p6, 3s2, 3p6. Oh, I forgot to put that in mine. 4s2, and then 3d9. In shorthand notation, or called the noble gas configuration, argon 4s2, 3d9, but in this configuration, the d orbital needs one more electron to fill this subshell. What happens is it pulls one electron from the 4s orbital, thus the electron configuration will become argon 4s1, 3d10. Yep, so this solution is correct. Okay, so on to question 3. What is the empirical formula of magnesium chloride if 0.96 grams of magnesium combines with 2.84 grams of chlorine? So first I'm going to write out the definition of empirical formula. So this is the formula that contains the simplest whole number ratio of atoms in a compound. Okay, so this is a multi-step question. So the first step is to find number of moles of each atom or element. So first, let's find the number of moles of magnesium. And we do that using mass over molar mass. So the mass of magnesium was 0.96 grams. And magnesium's molar mass, which you would just find on the periodic table, is 24.03 grams per mole. Okay, so you'll notice that our grams will cancel out. And we're left with our value that is in moles, which is around 0.39 moles. Okay, so that's the number of moles for magnesium. We can do the same thing for the chlorine. Okay, so mass over molar mass. So chlorine's mass was 2.84 grams. And chlorine's molar mass is 35.45 grams per mole. Okay, so this gives us 0.80 moles. So step 2 of the solution is to divide both mole values with the lowest number of mole. Okay, so I'm going to write out our formula. And if you look at which value gives us the lowest number of moles, it's magnesium. So 0.39 divided by 0.39. Chlorine's number of moles was 0.8. And I'm also going to divide that by 0.39. If we are to simplify this, it gives us magnesium 1, chlorine 2. But we don't actually have to write out the 1. And then this will be our empirical formula. Okay, so let's see what the junior tutor said. Empirical formula gives the simplest whole number ratio of atoms in a compound. If the mass of constituent elements are given, compute for the number of moles using the atomic weight of each. So they found 0.395 moles of magnesium and 0.801 moles of chlorine. Next step is to divide each of the number of moles with the lowest value obtained to get the subscripts for the empirical formula. Okay, so they got MgCl2, so this solution is correct. Okay, so on to question 4. The molecule nitrosyl chloride, NOCl, As a skeleton structure of ONCl, two resonance forms can be written. Write them both. Use the formal charge stability rules to predict which form is more stable. Okay, so first we need to find out the total number of valence electrons for all the atoms involved. So this will help us when we write out its structure. So for nitrogen, there are 5 valence electrons. Oxygen gives us 6. And chlorine has 7 valence electrons. And since there is only one atom of each, I don't need to multiply them by any numbers. I just need to add them all up. And you get a total of 18 valence electrons. So now I can try to write out the first structure. Okay, so let's recall that for each bond, there are 2 electrons involved. So chlorine will have the one single bond with its 3 lone pairs. So that gives us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons so far. I'll draw a double bond on the oxygen to give us 12. And then 13, 14, 15, 16, 17, 18 electrons total. So this is one of the resonance structures that you could have. Another one would be the following. So let's say this bond went over to that side instead. This gives us a single bonded oxygen that has a negative charge. And a double bonded chlorine that has a positive charge. Okay, so let's just show the formal charges for our first compound, just to show how all of them are neutral. So to calculate formal charge, it's going to be the number of our valence electrons. So for oxygen, there was 6 minus, however, electrons are non-bonding. So all the lone pair electrons, so that's 4. Minus, however, electrons are involved in the bonds divided by 2. So there are 2 bonds, and each bond has 2 electrons, so there are 4 electrons in total. Divided by 2 gives us 2. So 6 minus 4 minus 2 is 0. And then we can do the same thing for the nitrogen. Its formal charge is 5 minus 2 minus 1, 2, 3, 4, 5, 6. 6 over 2. So that gives us 0 as well. And then lastly, for the chlorine, it's 7 valence, 6 lone pairs, and 2 divided by 2, which is also 0. So if we did the formal charges for our second compound, we will get different values. So for oxygen, it will be 6 minus 6 minus 2 over 2, which is -1. For nitrogen, it is 5 minus 2 minus 6 over 2, so this is still 0. But for the chlorine, it is 7 minus 4 minus 4 over 2. So 3 minus 2. So this gives us +1. Okay, so since compound A has all neutral atoms, this will be the more stable resonance structure. Okay, so let's see what the junior tutor said. There are a total of 18 valence electrons in the atoms of nitrosyl chloride. 6 electrons are in 3 bonding pairs, while 12 are in 6 lone pairs. 2 resonance of nitrosyl chloride structures are as follows. Yep, and then according to the formal charge stability rules, resonance forms with more or larger formal charges are less stable. Therefore, the resonance form on the right side is more stable. Yep, so this solution is correct. Okay, so on to question 5. What are aromatic amino acids? Aromatic amino acids, as you can guess, are amino acids that contain an aromatic ring in their R group. Okay, so I'm just going to draw them all out. So this is the structure for tyrosine. You can see that it has an aromatic ring with an alcohol group. This one is tryptophan. This is one of the simpler ones. Called phenylalanine. Alanine, sorry. Phenylalanine. And then the last one is histidine. Okay, so let's see what the junior tutor said. Basic building blocks of an amino acid are the functional group, so the carboxylic acid group, and an amino group, NH2. For our different amino acids, there are specific R chains attached to it. This R chain is an aromatic ring. It becomes an aromatic amino acid. Some examples of aromatic amino acids are histidine, phenylalanine, tryptophan, and tyrosine. Yep, so this solution is correct. I'll just correct the spelling mistake for histidine. Oh god. Histidine. Okay, so question 6 asks, what is a polar molecule? So this is when the distribution of electrons between covalently bonded atoms is not even. So this may be due to some differences in electronegativity. I'm also going to add that polar molecules have an overall non-zero dipole moment. Okay, so the easiest example for a polar molecule would just be water. So I'll draw out the molecule of water here. So our oxygen is more electronegative than the two hydrogen atoms. So I'm going to show that there is a dipole moment going towards the direction of the oxygen. Oxygen is also slightly more negative, whereas the two hydrogens are positive. So this is a polar molecule. And that's due to the differences in electronegativity of oxygen and hydrogen. But I'm also going to add another example. So let's say we had carbon tetrafluoride. If I were to draw out the structure, obviously fluorine is more electronegative than carbon. But since all these fluorine atoms are equally surrounding the carbon, all these dipole moments cancel each other out. So CF4 has no dipole moment. So I'm just going to write out that the CF bond is polar since fluorine is more electronegative. However, the CF4 molecule is nonpolar. Since the dipole moments cancel out. Okay, so you want to make sure you look at the overall molecule before realizing that the carbon-fluorine bond is polar, since all the dipole moments can cancel each other out. Okay, so the junior tutor said polar molecules share a bond that is partially ionic and partially covalent called polar covalent bonds. Formation of partial ionic charges is due to the unequal sharing of electrons between two atoms that results in the difference in electronegativities. Polarity describes how different the electrical poles of a molecule are. The higher the difference, the higher the polarity. Water is the most common example of a polar molecule. Difference in electronegativities between oxygen and hydrogen atoms creates a partially negative and partial positive charge. Okay, so I'm also just going to add the CF4 example. So the solution's still correct. Okay, so solution is correct. On to question 7. What is the IUPAC name for the compound shown below? Okay, so I'm going to draw it out as well. Okay, so when naming compounds, I like to circle the longest carbon chain that has the most important functional groups. So in this case, the oxygen. And then I'm going to count out how many carbons are in our parent chain. So there are 1, 2, 3, 4. And then there's also a methyl group on carbon 2. So since the most important substituent here is the alcohol, I labeled its carbon as carbon 1. So now I'll just write it out. So on carbon 2, there's a methyl group. So I'm going to name it 2-methyl. And then since there are 4 carbons in the compound, I'm going to use the prefix bute. So it's 4-methyl bute. And then again, since there's an alcohol group, I'm going to end it with a nol. So this gives us an IUPAC name of 2-methylbutanol. Okay, so the junior tutor said the same thing. Explanation and chemical nomenclature. The IUPAC nomenclature of organic chemistry is a method of naming organic chemical compounds. Ideally, each possible organic compound should have a name from which an unambiguous structural formula can be created. In general, they'll have three essential features: a root or base, a suffix, and then names of the substituent groups other than hydrogen that complete the molecular structure. So they summarize all the different root names of the carbon chains that you can have. So in our case, there were 4 carbons, so that's where the bute came from. And here are all the different suffixes. So again, ours had an alcohol group, so we know that the IUPAC name will end in "all." Yep, but this summarizes all the different functional groups you can have. And then they give a very in-depth explanation of how you would do this. Yep, so this solution is correct. Okay, on to question 8. What is the formula for sodium nitride? Okay, so I'm just going to write out the name. So we're basically all familiar with sodium. It is Na+. But nitride, on the other hand, has the formula N3-. So therefore, we need 3 sodium ions to neutralize the -3 charge that the nitride has. So sodium nitride will be Na3N. Okay, so let's see what the junior tutor said. Sodium nitride is an ionic compound as a result of the bonding of sodium and nitrogen ions. Sodium belongs to group 1, and these elements have 1 valence electrons that it can lose, meaning it has a charge of +1. So we will have, I'm guessing they mean sodium ion, Na+. Nitride is an ion of nitrogen, which belongs to group 5, and these elements have 5 valence electrons and need to gain 3 more, forming an ion with a charge of -3. As they bond together, they form a compound with a neutral charge, so the charges must be balanced, and in order to do that, 1 ion of nitride needs to bond with 3 of sodium. Therefore, the chemical formula will be Na3N. Yep, so this solution is correct. Okay, on to question 9. Write the quantum numbers for 5 electrons of boron. Okay, so first I'm going to write out the electron configuration for boron. It is 1s2, 2s2, 2p1. So there are 5 in total. And I'll also draw out its diagram to show all the electrons. Okay, and I'll draw it in using red. So 1, 2, 3, 4, 5. Okay, so first let's look at the electron in the 2p orbital. So for the 2p electron, the N value is equal to 2. Since this is just the same number that is in front of, it's pretty much, since it's 2p, N is equal to 2. And to find out our L number, over here on the left, I'm just going to write out this helpful tool or chart. Okay, so these are all the possible L values. Since P is equal to 1, then our L is 1. Our ML is equal to -1, since the electron that is in that orbital, there's only the 1. And for the spin, you'll see that it is going up. So MS will be +½ Okay, so now let's look at the electrons in 2s. 2s electrons. Our N is still equal to 2 since we're looking at 2s. This time our L, if you go back to this table here, will be equal to 0 since it's 2s. And since our L is 0, our ML can only be 0 as well. And our spin, I'll just show that it can be both plus and minus half, since you see 2 electrons spinning in the opposite directions. And then lastly, for the 1s electrons, this time our N value is equal to 1. Our L is like the previous part, and it's equal to 0. ML will also equal 0. And again, our MS will be both plus and minus half. Okay, so let's see what the junior tutor said. According to the Pauli exclusive principle, no 2 electrons in an atom can have all the 4 quantum numbers the same. So an electron in an atom must have at least 1 quantum different from the other electron. Principal quantum numbers n can have values 1, 2, 3. Angular momentum quantum number L takes the values 0 to -n-1. L values for S, P, and D are 0, 1, and 2 respectively. Magnetic quantum numbers ML takes the values from -1 to +1. So that depends on your L value. So if you had an L value of 2, then the range would be different. It would be -2 to +2. But in the case of this example, it's only -1 to +1, since our L value is only 1. The spin quantum number ms takes the value +½ or -½ only. Atomic number of boron is 5. Electron configuration is 1s2, 2s2, 2p1. Okay, so they got n equals 2, L equals 1 because it's in the p orbital. ML has values -1, 0, and +1. But since there's only the 1 electron, they said that its value is only equal to -1 as well. And same with the spin. 2s electrons, 2, L equals 0. ML has value 0. MS +½ for the first electron, -½ for the second. Yep. And then for the 1s electrons, n equals 1. L equals 0 because L takes value only up to n-1. Yep. ML has value 0. MS has +½ for the first, -½ for the second. Yep, so I can say that this Solution is correct. Okay, so question 10 asks, what is the difference between an ether and an ester? So, when you have an ether group, this is when you have an oxygen that's in the middle of two carbon groups. So it doesn't matter what they are. So that's why I just denoted R as just random carbon groups, as long as it's in the middle and not at the end. So ester is similar. It is also found in the middle. However, instead of a single oxygen, it actually has some carboxylic tendencies, shown like that. Okay, so this is also in the middle. If it were a carboxylic acid, then there wouldn't be another R group, there would just be a hydrogen. And similarly, if this was an alcohol, for the ether, there wouldn't be another R group, there would just be a hydrogen. So those are the two structures. So the junior tutor said, ether is a functional group in which there are two carbon atoms single bonded to an oxygen atom. Figure shows below an example of an ether. On the other hand, an ester is a derivative of carboxylic group which contains a double bond between a carbon and oxygen atom. The figure below shows an example of an ester. Yep, so this solution is correct. I'll just also add that it can be any carbon R group. I don't know how to draw this. I'll write it like this. Okay, so this solution is correct. Okay, so we are on question 11. Calculate the molar mass of sodium sulfate. Sample of sodium sulfate with a mass of 300 grams represents what number of moles? Okay, so this is a multi-step question. So first, let's figure out the chemical formula for sodium sulfate. So sodium is Na+, and sulfate is a polyatomic ion that is SO4 2-. So therefore, we need 2 atoms of sodium to neutralize 1 sulfate, and we get Na2SO4. Okay, so step 1 is to calculate the molar mass of sodium sulfate. So this is going to be equal to the molar mass of sodium plus the molar mass of sulfur. So the molar mass of sodium is multiplied by 2 since there are 2 atoms of sodium, and also 4 times the molar mass of oxygen. Okay, so let's plug in all of their atomic mass values, which you can just find on the periodic table. Sodium, it's 22.99 grams per mole. Sulfur is 32.01 grams per mole. And for oxygen, it is 15.99. Okay, so adding all these values up give 142.04 grams per mole for the molar mass of sodium sulfate. So part 2 of the question asks, if the mass is equal to 300 grams, what are the number of moles? So to answer this, number of moles is equal to mass over molar mass. So the mass is given in the question, it's 300 grams, and the molar mass is what we found out in the previous step, which is 142.04 grams per mole. Okay, so if we divide this, we get a number of moles of 2.11. Okay, so let's see what the junior tutor said. They got a molar mass of 142, and for moles, they got 2.113. Okay, so this solution is correct. Question 12 just asks, what is the molar mass of sodium carbonate? So the molar mass of sodium carbonate would just be the molar mass of sodium times 2 plus the molar mass of carbon plus 3 times the molar mass of oxygen. Okay, so let's add these values up. So the molar mass of sodium can be found on the periodic table. It's just 22.99 grams per mole. Molar mass of carbon, 12.01 grams per mole. And the molar mass of oxygen is 15.99 grams per mole. So adding all these values up gives us a final molar mass of 105.99 grams per mole. Okay, so let's see what the junior tutor said. The molar mass of a substance is the sum of the molar masses of all atoms in the substance. For sodium carbonate, the molar mass is the sum of the molar masses of all sodium, carbon, and oxygen atoms. Their molar masses are 22.99, 12.01, and 15.99 grams per mole, respectively. Okay, so they got the same thing. So I can verify that this solution is correct. Okay, so question 13 is actually the same thing. Yeah, so I'm just gonna show this up. 12/13. Okay, so they also got 105.99. So this solution is correct. Question 14 just asks, what is the molar mass of helium? So you can just find this on the periodic table. The molar mass of helium is 4.00 grams per mole. And if we look at our junior tutor's answers, they say molar mass is the mass in grams, 1 mole of a unit of a substance. Yep, so they got the same thing. Question 15 asks, what is a neutral pH? So for a neutral solution, the pH is equal to 7. If you were to have an acidic solution, the pH would be less than 7. And for a basic or alkaline solution, pH is greater than 7. Okay, so the junior tutor said, a neutral pH means a pH value of 7. The acidity and alkalinity of a solution is measured by its pH value. pH range is from 0 to 14, with the mid-range of 7 being neutral. pH value of less than 7 indicates an acidic solution, while a pH value of more than 7 indicates an alkaline solution. Closer the pH value to 0, the more acidic the solution is, and the closer the pH value to 14, the more alkaline the solution is. Yep, so this solution is correct. Okay, so I think we have time for one more question. What is the molar mass of aluminum? Okay, so you can just find the molar mass of aluminum on the periodic table, and it is equal to 26.98 grams per mole. Okay, so let's see what the junior tutor said. Molar mass of any element can be identified by using the periodic table of elements. The unit of molecular weight in the periodic table is U, and is also equal to grams per mole. Thus, the molar mass of aluminum up to 6 significant figures is 26.9815 grams per mole. Yep, so this solution is correct. Okay, so that is all the time that we have for today. If you liked today's Q&A session and you'd like to be notified of when we do this next, then please hit the subscribe button and the notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you liked today's video, go ahead and give it a thumbs up and a comment, and don't forget to share it with all your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.